So I started. 1 second. Yeah, just 1 second. We'll check on you. Okay. So it's a great pleasure to welcome Dheeraj to TFR. It's his first time here. Dheeraj did his PhD from MIT, I guess, end of December 2021, right? Yeah. And then he's been with Google Research, he's doing exciting work in statistics, applied probability, and theoretical machine learning. And he'll tell us whether theoretical machine learning is more applied or applied probability is more theoretical.
Sorry, just 1 second.
Oh yeah.
Just want to make sure that the stream is on.
Is anybody online?
Yeah.
I'll be talking about stochastic approximations of sampling algorithms. I wanted to actually talk about 2 different algorithms here, but I don't think I'll have the time to do justice to both. I'll just pick my work on stochastic gradient Langevin dynamics, and then I'm happy to discuss in person after the talk about Stein Variational Gradient Descent. Okay, so joint work with Aniket, who's a pre-doc at Google, and Nagaraj, who's a postdoc at India and UAE. One more. You just have to click on the screen. Okay, so the topic which will be the overarching theme here is sampling in RD, the real space in D dimensions. Okay, so given an oracle of access to a potential function f, which maps R to R, we want to sample from the target density pi star of x, which is the Gibbs measure with respect to f, that is e to the minus f of x. F is kind of like the Hamiltonian. And then the challenge here is that in high dimensions, it's very hard to compute the normalizing constant of pi star because of the curse of dimensionality. There are too many disjoint open sets of constant radius, and therefore this is a hard problem in that sense in general. However, this is a very fundamental problem in machine learning and statistics, where it is very central to Bayesian inference, where you want to sample from the posterior. It is useful in theoretical computer science, in volume computation and algorithmic geometry, and it's also central to statistical physics, where we derive most of our notation and diffusion from. And then it's also right now found applications in differential privacy, that is, sampling from this kind of thing is called an exponential mechanism, and that it ensures privacy under certain settings. Okay, so what are the popular algorithms for this? So what we'll consider is called score-based sampling. Okay, so basically, score function is this gradient f, that is the gradient of the log likelihood of pi star. And then let's say we have access to grad f, we can evaluate grad f at any point we want. Can we sample from pi star? Okay, so popular algorithms are like Langevin Monte Carlo, which does Langevin design, but time discretized version of it. There is Hamiltonian Monte Carlo, which has a velocity term, and then it's kind of like tries to mimic a physical system going down with this potential. And then of course there's Stein Variational Gradient Descent, which is kind of like a variational spin on this, which is a particle-based method to do this. It has very little randomness in that it does. It's not a stochastic differential equation; it's an ordinary differential equation with samples. Okay, so let's think about Langevin Monte Carlo. So here there are 2 cartoons. The first one is, of course, the well-known gradient descent. If this is like the loss function landscape, so gradient descent would quickly converge to a local minima like this. However, stochastic gradient Langevin dynamics with f of x being in the exponential, the potential function would behave like this. Okay, so what is the update equation? This is basically gradient descent plus Gaussian noise. However, this is not like stochastic gradient descent. However, this is a discretization of a stochastic differential equation. How do we know this? It's because there is this eta parameter within the step size. The noise does not scale as eta, but it scales as square root eta, which is like the quadratic variation in a Brownian motion. So this has to be interpreted as the discretization of a stochastic differential equation. Okay, and yeah, so what it discretizes is called the Langevin dynamics, which is one of the most popular and canonical stochastic differential equations given by the following Ito differential equation, that is dxt is equal to minus grad of xt dt plus square root 2 dpt, where dpt is the Brownian increments, right? And we can show that under very general conditions that the Markov process given by dxt converges to stationarity as t tends to infinity, right? And this is done by pathwise theory and so on.
As stated, this is not reversible.
Yeah, I don't. No, I don't think so. No, but if you start at pi star, it should be right.
Start at pi star, yeah, but otherwise it won't be much work.
Yeah. Yeah, I mean, all Markov chains are reversible, but it's a time-dependent Markov chain. Right? By disintegration theorem, you can always reverse a Markov chain. But it gives you a time-dependent Markov chain depending on the initial condition. When it becomes time-dependent and the same is when it start at pi star.
I think what it means is the generator is not there. So yeah, I mean, you want that the probability of going from A to B multiplied by the transition measure, I mean the stationary measure at A is the same reverse A and B, right? So
yeah, it is reversible. When you start at pi star, yeah, it is reversible.
No, but reversibility is not it depends on where you start. When it says a property,
Finite Markov chains, reversibility is defined with respect to the stationary measure.
Yes, but yeah.
what I'm wondering is if the gradient is constant, then I think this looks fine. But otherwise, then because somehow the discretization in the scaling limit, I think it is reversible. But if you don't discretize it carefully, maybe it.
Oh, you mean this chain?
Yeah, that.
Oh, I don't think that. No.
So that is not.
That might not be. I don't know. I don't know the place. But this definitely is similar.
Will be close to reversible.
Still, if you want to prove something in the
Spectrum and all that.
Yeah, so it's not much is known about the stationarity and mixing properties of this. Maybe when it is strongly convex or something, when F is strongly convex, then you can have a coupling argument and nice properties, but I don't think that's
you might have to edit the chain also, right, to make it reversible.
yeah, I don't know much. Maybe yes.
Can you construct continuous SDs which also have the same stationary distribution and topward, which one is faster and which one is slower?
Yeah, I don't know. But we will do kind of an interpolation of this, like with a time-dependent stochastic differential equation, and that's how we will analyze it. But yeah,
There's no kind of literature on this.
yeah. I don't know if there's a G such that this stochastic differential equation becomes this like time-independent G, but we can make it like linear interpolation time-dependent F.
No, but I mean, for example, don't have a Brownian motion, but something more complex there.
That I don't know.
Just to enhance mixing.
I don't know if it will end up a Markov process in that sense, right? Because you'll need to know XK to update this. But yeah, I'll have to think a bit more about it.
This value diffusion.
Yeah, Yeah, so right. So now let's consider the stochastic approximation of this called Stochastic Gradient Langevin Dynamics or SGLD. So in many large scale problems, F has more structure, that is F, capital F can be seen as an expectation of some random functions over a probability distribution, right? It could be where this psi could be data, and we are integrating out this loss function over all the data from the ground truth probability or the empirical distribution. Okay, so so therefore, if we take psi from this probability distribution T psi, grad f of x comma psi would be an unbiased estimator for grad f for every x in that sense, pointwise sense.
So then are you saying that F is also an expectation of one F in the setting?
Yes, yeah. So let's assume that f is an expectation of that. It's I just used.
You want to then start to from exponential of expectation of something and you know the expectation.
Yeah.
That's a problem.
You or it could be expensive if you want. I might even know it, but it might be expensive to compute. For instance, if you have like a finite sum problem that is f of x is equal to 1 over n, summation I equals 1 to n f I of x, it's kind of like an empirical risk minimization kind of problem. And then it's very expensive to compute this. As in, even in the simple setting, you need O of nd computations per iteration, and it is almost never used in practice. And because n could be of the order, 100,000 or 1 million or something like that. So here is where stochastic gradient Langevin dynamics comes in. So if we can sample these psi IID, right? For instance, if it's a finite sum problem, you can pick random indices with replacement, and then take a batch of these estimators, unbiased estimators, and construct this approximation to Langevin dynamics. This is the stochastic gradient Langevin dynamics. Instead of grad of x, we replace it by its unbiased estimator. So this is better because if you choose a moderately large batch size like 10 or 20 or 100 or something, and this only requires O of dB computations per iteration, and this is very tremendously successful in Bayesian. Okay, so in this sense, we are doing a path space stochastic approximation of these stochastic differential equations. So like I said, it's in the path space. This won't make much sense unless I introduce you what the measure space stochastic approximation is, which I won't be talking about much in this, but I'll just briefly allude to that in this talk. Okay. So let me introduce you to the other kind of stochastic approximation, which we can consider. It is in something called the Stein Variational Gradient Descent. Okay, so here the update can be called a McKean-Blasov equation, but this is not a diffusion equation, it is a ODE. Right, so here we have dx by dt is equal to this velocity term g of xt comma mu t, right? Okay, so where k is some reproducing kernel, okay, and mu t is the law of xt, right? However, it is not clear how to write down computationally this differential equation, because if you try to track xt, we cannot track mu t because mu t is an infinite dimensional object, right? So we have to do some kind of a stochastic approximation to even discretize this or even write down this kind of a McKean-Blasov equation. So the standard implementations of this is via particle-based discretization. That is, we consider n particles xt0 to xt(n-1), they're evolving in time, and their empirical measure, we hope that it approximates mu t, the law of xt at time t. That's it. And then what we do is xt plus 1 I is equal to xti minus gamma g of xti comma mu t hat, right? We replace this mu t with mu t hat, and mu t is the empirical measure of these particles. Okay, this is very tremendously successful in practice, and there is no stochasticity in the sense that there is only propagation of chaos. There is no Brownian motion driving the system. Okay, there's only initial randomness, and then finally you end up with a sample. And it turns out the finite particle convergence rates are notoriously hard to analyze. And we actually give a principled way of doing stochastic approximation, not like this bootstrap within the particles, which probably converges to the right distribution, target distribution. I won't be discussing that here. It's called.
You started by signing this Gibbs distribution you want to sample from, and you got this dxt by dt, that expression.
Yeah.
And now you're going to tracking this xt. How is that related to getting a sample from that distribution?
Yeah, we can show that. This actually connects to Wasserstein gradient flows. If you both Langevin descent and this are similar, but this is kind of a projected gradient descent. You project the gradient onto a RKHS subspace, right? So there you would be it's in the L2, the gradient in the Wasserstein gradient, but here it's in the RKHS space. So it's a bit nicer behavior, and that's why you don't get the Brownian motion here.
Okay, you know.
Okay, yeah, K is any fixed kernel, like let's say RBF kernel.
So you just take the gradient about the simplify. So they just take you to be kx by just x dot y.
Yeah.
Then what happens?
So you can write some differential equation like this even for Langevin dynamics, right? But then you'll end up estimating the score function of mu t, like grad log mu t, which is not easily estimatable. But by projecting it onto the RKHS, you get this nice tractable form, right?
Is this like the expectation of some random process?
It's not an expectation of random process. So basically, you can okay. So
It's deterministic, right?
yeah, it is. That's the nice part about this. So you can write a deterministic version of even So you can write
Is
any.
it a process on the measure?
Yeah. So any process on the measure can be seen as a process on the path space with some velocity. However, generally the velocity field will be time dependent. Right, and then what is the time dependence? If you write that for the Langevin dynamics, the appropriate thing, the velocity field would consider grad log mu t, which you cannot estimate. But if you've been doing this kernel trick, you do this integration by parts, you take the gradient into the kernel. Right. So you don't have to estimate the score function of mu t.
So it just take K to be the utility, like the product.
Okay. Yeah.
So then that second gradient is just X.
Okay. No, I think let's take it to be Gaussian because you need to do integration by parts. It's not clear that will work out.
So
Yeah.
Basically got rid of having to take derivative of mu.
Exactly. Yeah. So by doing this, by projecting it onto the RHS space. Right. So
And you're assuming that G is calculable easily here?
yeah. So So correct. So G is a function of xt, which is here, and it's an integration with respect to mu t. Here I replace mu by the empirical pressure. It's just a sum. Right?
Yeah.
So, but this is notoriously hard to do it. It's very, very combinatorially complex. At least this discretization scheme. We can do something called virtual particle SVGD, which is probably convergent. I won't be discussing here. Right. So,
The original machine also had a Brownian motion. Is there any advantage in dropping it?
yeah. So the advantage is that you don't need to have randomness in it. So it's just pure propagation of chaos. Right. If you start with n particles with some distribution, you get a sample from the target distribution or close to the target distribution without adding any other randomness other than the initial. So it's a theoretical thing, and then of course you can see that it behaves beautifully in the sense that the way it discretizes is very different from the way Langevin dynamics does, and certain functionals are converge much faster with SVGD than with let's say SGLD or something.
But D must be very large in applications, right?
Yeah, yeah.
So, and N is definitely not going to be exponential in D. So, but you would expect that if you want to approximate a measure in RD, you require an exponential.
Exactly, that's the problem. Yes, that's one of the huge problems when you come to analyze this. So if you try to track this mu t with this mu t hat, you need exponential in D number of sample particles. So that's why you need to do the stochastic approximation. So uniform convergence is not the way to go here. Right? Yeah. So
For the Brownian case, that large deviation is as well as available.
yeah, I think so. Yeah.
I will know that it approaches.
Yeah, there's a lot of results on that. Yeah. So, but when they invented this, the whole point was to not have the Brownian motion, just pure different ODE to kind of get the answer, the initial randomness. Yeah. So going with this, so this is kind of like a sample from a mixture of Gaussians, right? The particles nicely tiled, they sit in the nice place, and then we get very nice pictures and very interesting combinatorial patterns out of this, which we don't know how to explain anymore. Right. So, okay, so this I call stochastic approximation in the space of distributions, right? And then we can do more principled way of doing this, and then maybe I'll discuss that in person if you're interested in it. Okay, so in optimization, stochastic approximation has been studied, and it's very, very successful, and we can obtain very sharp rates for in a large class of functions, for a large class of loss functions and problems. Okay, so can we do that kind of a trick here? For instance, sampling is actually optimization in the space of probability distributions, right? So for the kind of metric space we choose is the Wasserstein space, that is P2 of RT, that is the space of probability measures on RT with finite second moment, and it is equipped with the Wasserstein 2 metric, right? So which is defined as with respect to the couplings here. Okay, so how can we see sampling as an optimization problem? We consider the KL divergence between mu to pi star, and pi star is the unique minimizer of this functional, and we kind of do gradient descent on this, right? So actually it can be seen that the Langevin dynamics is actually the gradient descent in the path space of this functional, right, or gradient flow. Okay, and then what we are doing is kind of like gradient descent in the path space by Euler discretizing. Okay, so now with this in mind, let's go back to SGLD.
So I missed what happened in the last slide.
Yeah.
You said you go from sampling to optimization.
Yeah. So my point is, in optimization, stochastic approximations have been analyzed very nicely, and they converge nearly the same conditions as the population dynamics, for instance. Right. So okay, so can we bring that theory here? This has been lacking in sampling literature. So can we bring some of those ideas here and then try to do that? So for that it helps to look at sampling as an optimization problem, of specifically this KL divergence from mu to pi star. Okay, and then we can track this in infinite dimensional space and see what happens to our trajectories when we do pathwise stochastic approximation. Right. Okay. So now let's go back to the SGLD, which is the main object we are trying to understand. Right. So you have these dynamics, that is xk plus 1 is xk minus eta over b times this unbiased estimator of the stochastic of the gradient plus square root 2 eta epsilon k, which is like the Brownian motion over 0 to eta integrated. Right. So this is basically stochastic gradient descent on grad f plus some Gaussian noise, like large Gaussian noise. Okay. So this is of independent interest beyond sampling, and this is actually has very close connections to differentially private SVD, and this could be interpreted as noise injection for non-convex optimization, etc. Because sampling is several times used for optimization and to escape saddle points. So even from finite dimensional optimization perspective, this is quite interesting. Okay, so but the theory for this has been limited so far, and that's why we try to reduce that. So let me point out to you some of the challenges we face. Okay, so some of what they do is they use Bayesian theorem and show that okay, these two trajectories are kind of indistinguishable. However, using the Bayesian theorem to compare trajectory of Langevin dynamics versus SGLD has a problem that the rates diverge as k tends to infinity. At some sweet spot, they'll be very close, but then after that they start diverging to infinity, k will diverge to infinity, and then the implied total variation distance bound also diverge to 1 as k tends to infinity. So we want stable guarantees. That is, we want to show that even as k tends to infinity, we will still be close to pi star. Okay. So there are also very restrictive assumptions on grad f or f, the function, potential function. That is strong convexity or even dissipativity, which is not much better than strong convexity, which is kind of seen as strong convexity at the infinity among some others. And they also assume uniform Wormstadt in some works. That is, what do you mean? Uniform Wormstadt means that the radon derivative of the initial measure to the target is uniformly upper bounded, which is very, very stringent when you're doing unbounded domains. It doesn't even work for Gaussians with different variances. So, however, Langevin Monte Carlo can be analyzed with just logarithmic Soleil equality on f, right? And which is the standard assumption for Langevin Monte Carlo, and this is sufficient. So, there's a gap compared to optimization literature where we can show that okay, gradient descent and stochastic gradient descent converge under pretty much the same assumptions, right? So, why is there such a gap here? Can we bridge this gap? Is the question. Can we show that okay, under pretty much the same assumptions as when Langevin Monte Carlo converges, that SGLD also converges? Okay, so analysis also assumes more stringent assumptions. In some works, assume it's a finite sum problem that cannot deal with other kind of problems, and they also assume component smoothness, that is, the small f are uniformly smooth, right? Which might also not hold in practice. Okay. So we have some open questions. That is, can we derive stable convergence guarantees for SGLD without assuming uniform Wormstadt, which we will do? And then does SGLD converge under minimal isoperimetric assumptions like log Sobolev inequality and Poincare inequality, which also we show. And the next question is, can the convergence of LMC be a nearly sufficient condition for the convergence of SGLD? So this has to be SGLD, it's a typo. That is, SGLD converges to the target whenever Langevin Monte Carlo converges, but we can't hope to get stable guarantees under such general conditions. Okay. So what can we say about the behavior of SGLD for non-concave sampling without assuming any isoperimetric, like kind of like Fisher divergence convergence or something like that? I won't be covering this for the sake of lack of time. But yeah, I'm happy to discuss these results offline. Okay, so let's think about CLT structure in approximation error of SGLD. So actually, this is a much nicer situation than optimization because we have a huge Gaussian noise driving it, and I'll tell you exactly why. Okay, consider this iteration of SGLD where we can write this score function approximate as the signal plus noise. The noise is actually the empirical sum of zero mean random variables, conditionally zero mean random variables. Okay, so that means law of nk given xk hat is approximately Gaussian. So we can write central limit theorem and say that okay, it is actually closely Gaussian. And then let's say conditionally sigma of xk hat. Okay, and then this is driven by a noise which is very, very large Gaussian. Right, this is of the order eta over b variance, and this variance is of the order square root eta, square root covariance of the order square root eta. So therefore, if it was exactly Gaussian, we can just absorb this into the Gaussian noise. So therefore, what we can view SGLD as is LMC plus a slightly higher nearly Gaussian noise. Okay, so this is the viewpoint we'll take. So yeah.
So there is something, the second original noise was square root eta, right? And this is multiplied by eta, so when you combine them.
Yeah.
How did you get square root?
Oh no, it's a typo, it has to be that. Yeah, it has to be a. So again, that helps us because it's a very, very small correction. Because when eta tends to 0.
So this noise is something which satisfies PLT. That's
Approximately, yeah.
But probably the movements will not. It doesn't have that yet. The noise is not very kind of severe. It's not that severe.
Yeah, it's not factored. But I think we should be able to do that. Right now, I'm not assuming factored, but it should not. I mean, we can do piecewise thing. I mean, as long as there are second moments, we can have like. I'll show him in techniques that okay, we can just cut off the tails and then analyze separately. Analyze this.
No, but you'll assume second movements.
Yeah. No, I mean, I'll assume much higher, but only for technical reasons. I think we can future work. We can work on the movements. It's not a big deal. Okay, CFT absorbs the stochastic approximation noise in the Brownian motion. Okay, so that's the idea. Okay, so we can think of CFT hiding the stochastic approximation noise in the Brownian motion. So we cannot distinguish between LMC and SGLD because of that. Because if you're given Brownian Gaussian with Gaussian standard Gaussian versus standard Gaussian with a slightly larger variance and ask me to distinguish them, they're not statistically distinguishable. So therefore, it stands to reason that LMC and SGLD should not be easily statistically distinguishable.
So you're taking a sample average there.
Yeah.
And now you take lots of samples to get CLT to work.
Yeah.
So is there a trade-off? I mean, are you losing out because you're spending too much here? And
Actually, it holds for every batch size. So that's why you use very asymptotic series. Right. Yeah.
So batch size can be small as well.
Yeah. It holds for any batch size.
Did you optimize the batch size in some way?
Yeah, we do. I mean, but we'll write it for every batch size and say, oh, if you pick this, you'll get the best. Right. So that's why I said we consider non-asymptotic CLTs in Gaussian distance, that is Bayesian type rates. And then this leads to state-of-the-art rates under Bloch-Sobolev inequality. This is stable, no warm start, and low batch size, like square root D batch size it works, for instance. And we also get first known rates under Poincare inequality. And we also show that the convergence of LMC is nearly sufficient for the convergence, again, sorry about the typo of SGLD. And even we can relax it to weakly smooth F, right? We don't need to assume that grad F is Lipschitz. And we also come up with an algorithmic improvement here based on the CLT analysis. It's called the covariance corrected SGLD, which I'll introduce shortly. Okay, so we saw that this noise is approximately Gaussian, okay, and it leads to epsilon, this slightly higher driving noise. Okay, so Gaussian can be described by two things, that is covariance and mean. So if we can just estimate the covariance, we can go back and correct the noise. Right. So what we mean is that we expect that we'll be adding this much nearly Gaussian noise. So we just go and subtract the functions by using the covariance estimator. So we call this covariance correction. We correct it by getting a Gaussian. So we can use an empirical covariance estimator like sigma of xk hat, which estimates sigma of xk hat, given a condition on xk hat, which can be done with an additional batch of b size b. And what we can do is, okay, we expect to add an additional Gaussian noise. We just go ahead and subtract it from the driving Gaussian noise. So that when we add this noise, it just cancels out and then looks like a standard Gaussian operator. Okay, so, and we claim that this is a better stochastic approximation of Langevin Monte Carlo than SGLD. Okay, so to remind you of this, okay, this is the SGLD. And this is the covariance corrected SGLD, but this is computationally bad because it takes O of B square computation in this form. So because you need to estimate sigma hat of xk hat.
And they're converging to the same thing.
Yeah, they converge to the same thing, right? But at a faster rate with respect to the budget, yeah. It's a slightly better properties. Okay. So what we can do is we can just do first order approximation here, like square root of 1 minus delta is approximately 1 minus delta over 2, and make linearize this. And when the estimator has like rank 1 estimators, is based on ranks, empirical sum of rank 1 estimators, this can be again computed in O of BD computational complexity. So we're doing this Taylor series approximation, and this gets rid of the hardness of the extra D factor in the computation complex. It's not a big deal. Okay. Okay.
And so is that the reason for that is that there's always a beta.
Exactly, yeah. So that's why this is much nicer than optimization because there's a very large noise and the stochastic gradient noise is very small. It will just hide it. Okay. So this is stochastic gradient SGLD, this is LMC, and this is the covariance corrected SGLD. We show that CC SGLD converges faster than SGLD. Okay, we don't technically show that because you need a lower bound on convergence of SGLD. We just show that the upper bound for CC SGLD is better than the upper bounds for SGLD. Right.
And how does it compare with the non-stochastic?
Okay, so but then you probably don't talk about oracle complexity for the non-stochastic case. You get a factor of 10 if it's a finite problem, right? So it might not even be tractable to compute.
But the number of steps, of course, there'll be.
Yeah, you get an extra factor of 10. It's not even comparable in that sense. Yeah. Okay, so let's first think about the easier problem, that is, when can LMC imply that SGLD converges? We'll derive unstable rates by using random function representation. Okay, and then we'll go to stable guarantees later. Okay, so we ask the question: can the convergence of LMC be a sufficient condition for the convergence of SGLD? The answer is yes. It can be shown by showing the statistical indistinguishability of SGLD and LMC. Okay, let's dive into that. So what we'll do is, okay, we consider the trajectory x1 to xk plus 1 of LMC, and we consider the trajectory with the same initial condition of x hat 1 to k plus 1, that is the trajectory of SGLD. And we show that the trajectories, KL divergence between the trajectories are small for moderately large k, and then therefore their endpoint by data processing inequality, their outputs must also be very close. So this implies that whenever Langevin Monte Carlo samples from the target distribution, so does SGLD. Okay, so what does this mean? This means that no statistical task can distinguish SGLD from LMC with non-vanishing probability, right? So you just cannot tell whether I applied SGLD or LMC.
So what is the relation between the number of samples and the dimension? So N is going to be infinity, is it?
Yeah, we can. I mean, in stochastic approximation, if you use like without replacement sampling, yeah, without replacement sampling, it will tend to infinity. Like you just keep on running it, and it's an approximation of the population limit. But if you want to take the population level grad f, right, so that is not tractable at all. If you take empirical sum, you get a factor of n, and that would be more like empirical risk minimization kind of problem, and n could be like very large.
But when you say that this something convergence, if the convergence kicks in only when n is exponential.
No, that doesn't actually. It doesn't suffer because of dimensionality. Under certain assumptions, of course, under certain there are bad f where of course it has because of dimensionality, but not for.
Yeah. So what is upper bound themselves you're going to get up? I would have thought that it would be like some conditional like.
We will do that. Yeah.
Oh, so
Yeah, we basically do tensorization of k.
This is a standard way of showing closeness.
Yeah, this is like a discrete version of Gaussian also. Gaussian inequality, like Gaussian formula.
Well, again, that's a way of showing that two processes are similar.
Yeah, okay, divergence. Like it gives you random equidistant derivative between those, but we do a discrete version. Okay, so this is applicable to non-smooth problems, and this is very general. I come to more specific assumptions and show stronger rates later, but this is like the generic hammer which we are going to use. Okay. Okay, let's do the standard assumptions. Let's say f is smooth, that is gradient of f is uniformly Lipschitz, so it can have at most quadratic growth at infinity, which is not very restrictive. And then we have this almost sure growth condition, like you were saying, this is not, it's much stronger than the moment condition. But this can be relaxed much more. I think 6th or 8th moment should suffice. We didn't want to confuse the reader in the paper, so that's why we had this. But we can the standard trick where you consider one bound till some threshold and then do another bound below that threshold should work. Right. So
what is small f? That's so big F is the expectation of small f?
yeah, big F is the expectation of small f and psi is the randomness, right? And we assume that this is the amount of fluctuation you can have. Right? But we can have like 6th moment, 8th moment, I think 8th moment for this.
So there's no randomness in the right hand side, right?
Yeah, there's no randomness. Yeah, this is almost sure. That's it. Okay, so we also assume that the moment growth condition, that is SGLD, satisfies the following for some p greater than or equal to 1. Let's say it doesn't have to have all the number of moments, it's just that x needs to be nice about like the moment of xk should be of the order e to the q over 2, the qth moment. So this is like saying we will actually use p equals 4 or 6 or 2, right? We won't go much further than that. We don't need many higher moments, and it can be shown by various techniques under various assumptions. So why is this d to the q over 2? It's because if each coordinate is of the order 1, then the second norm will be of the order, like qth norm will be of the order d to the q over 2, right? Qth norm to the power q, right? So therefore, this also makes sense. Okay. So these are mild technical conditions, and this is weaker than dissipativity used in previous works. Okay, and we can remove this for finite sum problems. That is this assumption, right? Non-standard assumption can be removed for finite sum problems using adaptive batch size. That is, when I detect that the variance is high, I can just make my batch size a little higher so that I don't need these higher order moment conditions. Okay. Okay, so let's state the first theorem. Okay, so statistical indistinguishability of SGLD and LMC. That is, let's say SGLD iterates are x0 to xk, x hat 0 to xk, and LMC iterates are x0 to xk. And under the assumptions of smoothness, almost sure noise growth, and moment condition with p equals 6. That is, there are up to 6 moments of the SGLD iterates. Okay, we can show that KL divergence between x hat 1 to k to x1 to k is at most eta square d square k over b square plus eta cube d to the 6 k over b to the 4. Okay.
So what's b?
B is the batch size. Right. So you would expect that in optimization you would get 1 over b here because that's the amount of variance you are adding, and KL divergence is kind of like quadratic in some sense. So you would expect a 1 over b, but because we are using a CLD, it is actually better. It's 1 over b square, right? And this is one of the reasons we get better results. Okay. So what this shows is that when k is moderately large, then eta k is sometimes constant, let's say, and so LMC convergence of LMC is nearly sufficient for the convergence of SGLD. Only additional thing we require is this moment growth condition. If we can show that the trajectory, the moments are not too high, then we can show that if LMC converges, then so does SGLD. Right. So this gives us a universal approach or near universal approach to show TV guarantees for the last iterate of SGLD. Right. So what we can do is pick eta and k such that TV of xk to pi star is of the order epsilon, and then b such that KL between these trajectories of the order epsilon square, and then by Pinsker's inequality we can show that our SGLD iterate is last iterate is also close to the target distribution. Okay.
So you got that b square in the denominator because of that covariance adjustment.
Yes. Okay. Yeah. So let me explain that a bit more closely. So here there are two errors, which I'll explain in more detail when I go to the proof. Is that this is because of the CLD. This comes because of the Bayesian type CLD, and this comes if it was actually driven by a slightly higher Gaussian inverse. Right. If you compute the KL divergence between Gaussians, and then if it was driven by a slightly higher Gaussian inverse, this would be the error, and this is non-Gaussianity caused with.
You had said somewhere that you estimate covariance and correct for it.
Yeah,
That's somewhere.
Yeah, and then that's the next result. That's next to this plot side. Okay. So this is the covariance corrected. So under the same conditions, what we did was we corrected for the covariance. We added a covariance estimator with batch size b. So here you can see that there's b cube instead of b square, right? So you have a slightly better covariance match. So you don't suffer the same consequences of using different covariants to drive the differential SGLD. Right. Okay, so this is the result. Okay, so this gives you better dependence on the patch size, that's 1 over d cube than theorem 3, that is previous one, which is on SGLD. And CCSGLD is a better stochastic approximation than LNC, at least going by the upper bounds. You would need a solid lower bound to show that, okay, this is in fact better. Okay, and this gives you improved oracle complexity in okay. Okay, so let's discuss the oracle complexity. That is, similarly, we can show that LMC has at xk has TV distance of O epsilon and K divergence between them is O epsilon square. Then we know that this converges to target in TV distance with error epsilon. Okay, so under Poincare inequality and Loxobel inequality, we obtain the following rates. That is oracle complexity of d to the 10 over 3 over epsilon square to obtain epsilon TV distance, and oracle complexity of d to the 4 over 3 over epsilon square under Loxobel inequality assumptions on the pi star on the target distribution. Okay. So yeah, so we have these kind of guarantees. I'll get into more about the functional inequality based thing. We can do much better than these forms there. Okay, so we have a faster convergence in factor of dimensions, but we have unstable convergence guarantees. That is, this depends on k, the k divergence performed. So as k tends to infinity, this diverges to infinity. So if you keep on running the algorithm, you don't know where it is as per these upper bounds. So that is the disadvantage of this. Okay, let me quickly sketch the proof of this theorem. That is, let's say LMC has its update, which I showed, and then we have SGLD update, which is like this. Okay. So they have the same random function approximation representation. That is, x1 to xk can be seen as a function of x0, the initial point, and epsilon to epsilon k, epsilon 0 to epsilon k. That is a Gaussian noise switch orbit. It's a measurable function of the noise switch orbit and the initial condition. Okay. What we can say is we can have the same function hk for SGLD as well. We have the initial point, and instead of epsilon k, we have z hat 0 to k. What is z hat 0 to k? Oh, I didn't define it as it. Okay, z hat 0 where z hat is epsilon k plus eta n, square root eta n k. Right, square root eta over 2n, sorry. Right, sorry about the typo. So therefore, this is basically saying it is being driven by a slightly different process. It's a Markovian process driving it instead of the Brownian. Right. So since law of x0 is equal to x0 hat, we can do KL tensorization. Right. So and then we can write KL between x hat 1 to k to x hat 1 x1 to k is less than or equal to expected KL between z hat k and fk, where fk is the sigma algebra of okay, this has to be small k, another typo. Where x this is the trajectory uphill time t, and then conditioned on that, z hat k should look approximately Gaussian. So what does this mean? This is an entropic CLD. Okay, so random function representation plus data processing inequality gives us this, and proving that this is close to 0 implies that we are trying to show an entropic CLD for this quantity, that is z hat given fk. Okay, so let's show this entropic CLD. Okay, so we can show that using some kind of a reverse T2 inequality for Gaussians, like we can do Gaussian splitting and come up with this formula where we can decompose this KL divergence between z hat k given fk to epsilon k as T co plus P CLD, where T covariance is because of the covariance mismatch. That is what we actually drove this with respect to identity covariance versus with this slightly higher covariance, which was because of the stochastic gradient noise, but exactly Gaussian. So what would be the difference? It would be this kind of a quantity. Okay, so this is kind of easy to bound because both of them are Gaussian, so it's same mean but different variance. So it's not a problem. And then we have this TCLT, which is we have this slightly higher covariance, I plus eta sigma k y, which is here. But we don't have Gaussianity, we have approximate Gaussianity. So what is the cost of approximate Gaussianity here is captured by TCLD, where x and y are Gaussians. Okay, so controlling T covariance is actually very simple. We have standard formulas for Wasserstein distance between Gaussians. You can even see it using KL and KL divergence and using information transportation inequality, and we show that it is eta square d square over b square. And this is the origin of the first term, which scaled as 1 over b square. Okay, and then for the TCLT term, what we do is we see that nk given fk is an IID average of zero mean almost surely bounded random vectors. Okay, we can use the central limit theorem, like Bayesian type central limit theorem, and see that this is approximately equal to normal of I plus eta sigma k. So this can be made more rigorous using Wasserstein CLT for Gaussian smooth bounded random variables, right? This is based off of Alex Zai's work from 2018, which shows very nice bounds for W2 convergence of CLT in high dimensions. And we show that TCLT is at most eta cube b to the 6 divided by b to the 4. And this captures the non-Gaussianity cost we pay because of this. And this is very rapidly decaying because of the b to the 4 factor. Okay, combining everything, we get the following bounds. Okay, so and CCSGLD, similar steps, but we can show that because this covariance is slightly better, we get a 1 over b cube instead of a 1 over b squared. Right. So therefore we get this nicer bounds for this T covariance.
You also do adaptive batching. Does that make sense?
Yeah, we do adaptive batching, but in a different context. We didn't consider that here.
Intuitively, how would that work? Would it be like small batches in the beginning, bigger batches later? Or?
No, it's like because we assume that if magnitude of x is large, then the noise might be large because we're going very far off. So use a larger batch so that you have a smaller noise. So it removes the moment assumptions on x because it cancels out some things. But in expectation, we can show that it's not too bad.
So roughly, how does the adaptive structure might look? And say, you think it will be large with the crazy?
No, yeah, it's like normic scale, like constant time normic case, theoretical thing we use. So it removes the assumption on that we need 6 moments or 4th moments, etc. We don't need any of those.
That's a good reason.
Yeah. Okay, so let's now look at stable convergence guarantees. So right now all the guarantees were unstable. That is, they diverge to infinity as k tends to infinity.
You can interpret it as saying that if you have passive b, then you should run for no more than about b squared.
No, not really, because we have step size is small, right? If you go to the
What step size is also?
yeah, so to give you intuition here, right? It's eta square k over b cube.
Right, is the correct.
Right, eta k is like time constant of the system. So, but there's an additional eta term. So there's eta over b cube actually. So batch size would be 1 and it would still converge to eta. Okay, so stable convergence guarantees. Okay, so to think about stable convergence guarantees, let me give you some background of why we need functional inequalities and why they were considered. Okay, so the classic duality, rather classic, the separation results here show that log concave sampling is easy when when f potential function f is convex. Sampling is easy. There are many algorithms to do it. However, when it is non-log concave, in general, it is hard. It could be NP hard for us. Right, the sampling problem is hard. Okay, this is computationally tractable and it is not. This can be efficiently sampled by a Langevin Monte Carlo. However, we can show that lower bounds at LMC and Langevin dynamics can take exponential time to escape certain local minimum. Okay, so this is kind of related to. This is kind of related to convex optimization, where minimizing a convex function is easy and there are nice algorithms to do it. However, in general, non-convex optimization could be HP hard or NP hard. There are so many results which show that it is very hard. So this is kind of the exact equivalent. So what we come to rescue is that so we can actually generalize this a bit more than log concave. It's called using isoperimeter. Right. For instance, there are functional inequalities. Okay, so called Poincare inequality and log-Sobolev inequality, which is how the expectation of functions behave with respect to the base integer. For instance, The Poincare inequality says that for any Lipschitz, for any function g, expectation the variance of g of x, where x is distributed as pi star, is bounded by this gradient quantity. So therefore, we can bound the expectation, how nice the function, an expectation of function is, by how smooth the function is. That is, if the gradient of that is well behaved, then the variance of this function is small. Loxo-Sobolev inequality is Poincare inequality of steroids. That is, we have the entropy function. We have this extra log g square factor here, but the same thing, but there's a different constant here. In fact, Loxo-Sobolev inequality is stronger than Poincare inequality. Okay. So Loxo-Sobolev inequality is weaker than strong log concavity. That is, all strongly log concave distributions satisfy the LSI. So we are relaxing the log concavity assumption here. And Poincare and Loxo-Sobolev inequalities are preserved under arbitrary perturbations, bounded perturbations, and Lipschitz. Like for instance, this is log concave. Let's say this looks like the Gaussian. However, this is not log concave if you do this kind of perturbations, but this is still isothermal, right? So it is stable to these kind of small perturbations. So it would be nice to study it under these conditions. And LSI, of course, is stronger than Poincare inequality. Okay, so to analyze this, we will have to connect under these conditions. We want to connect it to optimization, right? For optimization, we go back to Wasserstein gradient. So that is what is the how we want to interpret that as optimization problem in the infinite dimensional space of distributions endowed with the Wasserstein metric. Okay, so we can define gradients in P2 of RD for certain functionals of the probability distributions, and we can analyze gradient flows and their discretizations, and intuitions from gradient-based optimization in RD that finite dimensional spaces can carry over, and we can use those ideas to get good bounds here. Okay, so Jordan, Kinderleiter, and Otto in their landmark paper showed that Langevin dynamics is a Wasserstein gradient flow of the KL divergence. Right. Okay. So that is if you consider the gradient flow of this, that is the KL between mu to pi star, the resulting trajectory models is actually exactly equal to the evolution of the probability distribution of the Langevin dynamics, the stochastic differential equation continuous time. Okay. Okay. So here we can consider the gradient with respect to the Wasserstein metric to be grad log mu over pi. Right. So these are the densities, assuming that mu has a density. Square of this expectation with respect to mu is the Fisher divergence. Okay, and Fisher divergence is given by this formula, and this is actually equivalent to dxt is equal to minus grad of xt dt plus square root 2 pt in the path space, and this has to be mu t. Mu t is the law of x. Actually, rho t is the law of xt, and this implies that d by dt of kl between rho t to pi star is equal to minus Fisher divergence of rho t to pi star. Right, Fisher divergence is a positive quantity, and along this trajectory, we have a decrease in KL divergence to the target distribution. Okay, so this allows for simple convergence proofs for Langevin dynamics under isothermal. Then this is famous Bangalore theory, which was later revisited by Otto Villani, Otto Kinderleiter and Jordan from the optimal transport perspective.
So this kind of this result from Jordan and all,
yeah,
that has come mixing rates of Langevin.
Yes, yeah, no, I mean it can be done with other ways as well. Like for instance, Bangalore theory can just give it very easy.
Okay, this doesn't give you anything more than that.
Yeah. So actually, I put this slide in because I wanted to explain SVGD as well. There, this kind of perspective is very important because there is projected. But here, you can also do it with more from first principles perspective. Just differentiate this and take the Kolmogorov equations of this and then see what happens, and then you just get that answer.
And then you have generic stochastic approximation. You can't talk about their distribution converging in this nice sense, right? Does it idea generalize in some way on Langevin distribution?
Yeah, I mean, they consider, for instance, training mean field limits of training neural networks. There is also this gradient flow in the certain case of distribution, right? And there are a lot of interacting particle systems which can be seen in this sense, and they were trying to originally solve those problems. And this is one of the applications. It is gradient descent in a certain time space. Okay, so from sampling to optimization, so we want to ask the question: is isoperimetry sufficient to ensure fast convergence of Langevin Monte Carlo, that is time discretized version? And the answer is yes, and it was shown by a sequence of papers. and it enjoys a very fast rate under KL divergence and under general Renyi divergences. Okay. So the approach they take is interpret sampling again, as I said, as an optimization over the space of probability distributions. Okay, and we now consider sampling under isoperimetry, right? So there exists no, so if the rough equivalence here is the PL condition, the Poilievre-Loessier functions. Okay, so there exist non-convex function classes that are minimized efficiently by gradient descent. So the duality is not convex versus non-convex. There's a much finer kind of separation. That is, there are some non-convex functions which can be efficiently minimized. Like for instance, the PL condition. Okay. So what classes of non-block concave densities can be sampled is the those satisfy isoperimetric conditions. Okay, again, like I said, it's the Poincare inequality and Loxo-Poilievre inequality, and these have been studied classically for the continuous time by Bakri and Emery. Okay, so let's go through the proof. Okay, so we had this Langevin dynamics, and if rho t is the law of xt, then we can show that the dkl by dt given pi star is equal to minus Fisher divergence of rho t given pi star, and where the Fisher divergence is equal to grad log mu over pi star squared. Okay, expectation with respect to mu. This can also be seen as the non-squared of the Wasserstein gradient in the Wasserstein space. Okay, and this allows for simple gradient convergence. So for instance, Loxo-Poilievre inequality is kind of like the PL condition, right? So what we can show is that Fisher divergence is at least 2 times lambda LSI times KL between mu to phi star, right? So therefore, this is like the gradient grows whenever the function value difference is large, which is exactly the PL condition, right? And we show that the gradient is bounded below, and then we get back to this differential inequality. That is dkl by dt is equal is less than or equal to minus KL 2 lambda LSI times KL between these terms, and applying the Gromfall lemma, we arrive at this exponential decay of the KL divergence along the trajectory of non-Langevin dynamics.
This is also how the standard proof from LSI to pathway.
Oh yeah, exactly. Yeah. So this was required for SGLD, but this you don't need to go through the heavy hammer of Wasserstein gradient. Yeah. Okay, so this mimics the proof of gradient flow under PL condition, and intuitions from optimization can be translated to some. Okay, so let's look at some assumptions. So smoothness and LSI won't cover Poincare inequality now, but it requires a bit more refined arguments. Let's suppose that we have LSI conditions, and we assume that the sub-Gaussian growth of the noise, we don't necessarily restrict to bounded noise here. Okay. And the moment growth conditions are still there for some p greater than or equal to 1. This satisfies the qth moment is of the order p to the q over 2. Qth moment is over t, that is. Okay, this is a mind technical condition similar to that, and we can remove it using adaptive batch cycles. Okay, so what we show is that under these assumptions, with moment growth for p equals 4, we can show that when eta is less than or equal to lambda LSI by 6L squared, this ensures that it doesn't diverge to infinity in some sense. The law of xk hat to pi star is less than or equal to e to the minus lambda eta k over. This is like the exponential decay with respect to the initial condition, KL with respect to the initial law, plus these approximations, right? Because we use time discretization and stochastic approximation. Okay. So the oracle complexity here is that if you want KL law of xk hat to pi star to be less than or equal to epsilon, you need to have an oracle complexity of d to the 1.5 over epsilon. And the parameter choice which achieves this is that you take eta to be of the order epsilon over d, and then b is of the order root d, the batch size. Root d is not a bad batch size in moderately large dimensions, and then k is of the order d over epsilon. Okay, this is the first stable guarantee for SGLD without any warm start assumptions. And same functional assumptions as the LMC guarantees can hold. And moment growth can be removed using adaptive batch sizes, so it works with the same assumptions as the normal LMC guarantees. Okay, so the main point here is that it's a stable guarantee for SGLD. It does not diverge infinity as the number of iterates between them. Okay, and this is the state-of-the-art oracle complexity in the strongest metric with lowest batch size. And this has faster rates than what is proven for fancier algorithms like variance reduced SGLD. People have proposed variance reduced SGLD, but this is actually faster in terms of the upper bound.
Can you just say something about this moment growth can be removed with finite assumption? Exactly how do you just comparison? What do you look at and then decide to piece of that?
Oh, you just look at xk. Okay, and then take basis to be some linear function of
Linear function?
normal scale.
No, scale. So whenever x scale is large,
Yeah.
is the bad size.
Yeah, when it is too large, I think you can just use n or something. Like it's a finite problem and you get 0 noise. So you just cut off the tail. So that will just remove this p equals 4 condition and we don't need any conditions. And in expectation, it has the same model. We can. Okay, so this is the comparison to state to the results. For instance, Adinsky et al. Considered component smoothness and dissipativity, and they had worse dependence on the dimension and epsilon, and then Zhu et al. Had worse dependence on dimension, and they also have Warmstadt assumption and component smoothness, and it was in PV. We actually improved along all those dimensions in dimension dependence, batch size, and in the metric of convergence and the assumptions in various ways. And it is actually better than the bounds on SVRGLD, that is variance reduced stochastic gradient Langevin dynamics. Okay. So the key ideas behind the proof is that we want to analyze the time discretization of the Wasserstein gradient flow with the same similar machinery. So we want to control the gradient noise by its CLT stuff. I think the time is almost up. Let me go quickly. So what we do is we construct this interpolating process, the linear interpolation. So we use the scale gradients, that is, we consider dxt is equal to minus grad f of x k eta plus noise times dt plus square root 2 beta t in this time interval. And we use scale values. So this is not exactly a continuous time Markov process because we are using cold values. There is some memory there. And then mu t, let's say, is the law of xt of this linear interpolation process. So this construction is adapted from prior work, which is Bangalore and Bayesian from 19, and then this is a piecewise SDE with UK eta is exactly being the law of x. Okay. The Jacob theorem, which is reproduced here, says that dKl by dt is equal to minus Fisher divergence. For the interpolating process, okay, we have a piecewise linear approximation. We will write a version of this. Okay. So here we can show that dKl by dt of mu d of this linear interpolated process is minus half Fisher divergence plus this discretization error. So what is the error we caused by using scale values of xt, that is xk eta instead of xt? And the next one is the stochastic gradient error, that is this expectation, conditional expectation of this noise given xk eta and xt. By adding this noise, how was that? Okay. Discretization error is actually pretty easy to bound, and using the Markov process of generators, we can show that this is bounded above by the Fisher divergence. So this is not a problem. Okay. To control the stochastic gradient error, now let's look at when x k eta is an IID of zero mean random vectors. Law is approximately the Gaussian. If it was exactly Gaussian, we can use the formula for conditional expectation of Gaussians and show that this is equal to eta times trace of sigma of xk squared divided by b squared, right? So this follows from precise computation of the conditional expectations, but we don't have Gaussianity. How can we still do this computation? We come up with and then due to subgaussian moment growth and subgaussian growth and moment conditions, this is of the order eta d square over b square, which is exactly what we wanted. Okay. So now we don't have the law, that is by central limit theorem. We want to show that this is approximately equal to that. We will still show that this expectation is less than or equal to eta d square over b square. So for this, we prove a conditional CLT type result. This is much weaker than a conditional CLT, by the way. We just show that using chi-square divergence that this quantity, this conditional expected quantity, is of the order eta d square over b square. Okay, and this actually uses the CLT that it is an IID sum of zero mean random vectors, and because of that, this conditional expectation is small, and this has a trade-off of 1 over b square. Okay. So then the descent lemma becomes dKl by dt is minus 1 over 4th Fisher divergence plus the time discretization error plus the stochastic approximation error. Right. So we get these three things. And since LSI is a PL condition on the Wasserstein space, we have the same Lox-Sobolev inequality, that is Fisher divergence is at least the KL divergence, 2 lambda times KL divergence. And so therefore we have this kind of a Grunwald time evolution, and then applying Grunwald lemma, we end up with this kind of a convergence result where the initial condition decays exponentially, and then we have this residual stochastic approximation error and plus time discretization.
So your earlier result about the K divergence between the two, will also give something of this kind, but very weaker, right?
Yeah, it's not. This is stable. Like as K tends to infinity, this does not diverge. So we give you a valid result.
No, but there also this, but you don't have this result that the mixing is mono.
Yeah.
Okay.
Yeah. So here
You can't say that I will stop at this K and everything else.
Yeah, you can just keep running and you'll still get good guarantee.
No, saying even there you could do that. You say I stop at a certain K.
Yeah.
I get certain guarantee, and usually Markov is because you have the actually that this correct.
Oh yeah, there's finite Markov.
No, any Markov thing, the session distribution correct, then the TL divergence will decrease.
Yeah.
But here you don't have that.
Yeah. It is not a stationary distribution of this, it's an approximation. That's the problem. We can't just spread it for
You're tracking something which behaves well, the Langevin dynamics, but you're not tracking it by a process which is very well behaved.
Correct. Yeah, so we are tracking an approximation of that, but using the same EVI, that is the same K change in K divergence. So that's the. So to conclude, we analyze random batch approximations of stochastic gradient based sampling algorithms. Error due to stochastic approximation is nearly Gaussian due to CLT. It can be absorbed into the diffusion term whose increments are exactly Gaussian. This gives a state-of-the-art convergence analysis and algorithmic improvements. There is the covariance corrected SGLD, for instance. Thank you. I can have any question.
Lots of questions all the talk.
So the pure gradient descent without the stochastic correction, there are no good analysis because that's what we said in the first two slides that is the noise term that you're adding helping you not have exponentially many particles in these things?
No, it's just no noise. Which noise are you talking about? Is it the stochastic gradient noise or the Brownian?
I don't know which is it. Both very similar to me, but
Okay, so it's like. Yeah, no, that is actually part of the problem. Yeah. So here there are two sources of noise, right? This is the stochastic gradient noise, and this is the driving Brownian noise.
yeah, so I'm saying if you don't have a driving Gaussian motion.
Oh, it becomes an optimization algorithm.
Yeah, it's an optimization algorithm, but the infinite dimension thing is an optimization algorithm, right?
Yeah.
So can you don't have a analogous thing where you have that optimization algorithm in finite dimensions approximating the infinite optimization algorithm.
Right, so the scaling limit is different in some sense that you have like root eta here, so it won't allow it to converge to a point. Right, but there is stochastic approximation where as you decay the if you have this standard conditions on eta t, right, it square summable plus but diverges some diverges, it will converge to a point mark which is the local minimum or the global minimum.
There's no deterministic analog, you put some repulsion or something between the particles.
So for that, yeah, you can actually that's the beauty of Stein Variational Gradient Descent. So the Stein Variational Gradient Descent was actually very highly regarded because it is one of the deterministic sampling algorithms. The only randomness is for this algorithm, right? So this is actually an ODE, and if you track the ODE with a random initial condition, you will actually end up with a sample from a distribution. So you don't keep adding noise. So in that sense, that's why this was like a big thing recently.
No more questions. Thank you. Very substantial work.
Yeah.